All right, guys, this video is meant to be a all-encompassing view of Trig. Hopefully we can get kind of a good view of it in about 20 minutes or so. Hopefully you don't need all pieces of this as well. Timestamps should be below. So let's begin with Trig. Okay, so right here, I've got a triangle inscribed inside of another triangle. So I kind of pace out this smaller one right here with another color. What you should obviously see is that they have the exact same angle right down here, both the purple one and that peach one. And now the trig that we're going to do is going to be focused on 90-degree triangles. We're not going to worry about the other ones. There's certainly more rules than that. And if that left angle is the same and the 90 degrees the same, then we can be pretty sure that this angle up here is exactly the same as well. Now, if the angles are exactly the same, then the first thing that means is we can call them all similar. Similar. Cool. And the main thing that gets out of that is that every single one of them have the exact same ratios. If you understand right there what I wrote on the board in purple, that's the basic gist of trig in a nutshell. Okay, I'm going to give some numbers to this for smaller triangle. Let's say that's 3, let's say that's 4, and let's say that's 5. Okay, I could then say, okay, how many different combinations of numbers are there? And you can go, well, I could go this one and this one, that'd be 1, and then this one and this one, that would be 2, and then the other 2, that would be 3. Or I could flip all of them, and in total I would have 6 at the very end. But let's give names to these. Okay, let's say, all right, this angle right down here, the one on the opposite side, this 3, let's call this, that's opposite of the angle. This 5 here, well, that's obviously the hypotenuse. It's already got a name. Okay, so the long side of the triangle is the hypotenuse. And then this one, somebody might say, hey, let's call it adjacent. It's right next to that angle. And to counter them, somebody might say, well, we already have another one that's adjacent. They're both right next to it, and it's just the one that's not the hypotenuse is the adjacent, the small side. Then we could combine them. We could say, all right, let's go opposite over hypotenuse. That's one combination, right? We could say adjacent over hypotenuse. That's another combination, and opposite over adjacent. And we'll give them fancy names. The first one, of course, we'll call the sine of the angle. The second one is the cosine of the angle. And the third one we'll call the tangent. But that's all cosine, sine, and tangent mean. All they are is, hey, pick these sides so that we all agree about what sides are being picked. Even if you don't know the angle that's down here, if you know all the sides, you should be able to do sine, cosine, and tangent. For example, in this triangle, the sine is just the opposite, 3 over 5. And the cosine is the adjacent over 4 over 5. And the tangent is the opposite over the adjacent, or 3 over 4. And when you punch these numbers into your calculator, that's all that's happening, except they don't tell you the fraction. Usually they say 0.6, 0.8, and 0.75. And you might go, oh, there's not two numbers there. Oh, yes, there is. This is 0.6 compared to 1, 0.8 compared to 1, and 0.75 compared to 1. So if I'm looking at the sine in this particular case, what this number says is whatever my hypotenuse is, 60% of it is going to be on the opposite side. Now, how did we get these particular, actually I'm going too fast. Let's go one more step back. So then, if you knew all the ratios, like we do on this small triangle, what if we have this bigger triangle and we know one side? If I know, say, for example, this side over here is 6, I can see these numbers have doubled, which means that same thing should apply to all the other numbers. This should go, I don't know why I decided that it was going to be meters there, 5 should go to 10, and 4, well, that should just go to 8. And that's your basic gist of trig. If you know the angle, then you should know the ratios. So if you have the angle and one side, you should be able to get everything else. But like I said a second ago, how'd they get those ratios? So what I've done here is I took a picture of this drawing that I made, and I used a protractor to measure exactly 30 degrees, and I measured the length of the line at 25 centimeters. And then I measured the other sides. The bottom side was 21.5 centimeters, and over here on the right side is 12.6 centimeters. And just like we did before, just a second ago, I could say the sine of this angle is opposite 12.6 centimeters over hypotenuse, 25 centimeters. And the cosine of the angle is that 21.5 centimeters over 25 centimeters. And the tangent of the angle is just 12.6 centimeters over 21.5 centimeters. Then I actually use my calculator and figure out what the cleaner number of this. This first one up here ends up as 7.504. This one ends up as 0.860. And this one ended up as 0.586. And that's pretty darn close to the actual numbers. It wasn't perfect because, like I said, I used a ruler and a protractor and it wasn't exact. But the actual number on here is, switching colors here real quick, maybe, is 0.500. This one is 0.866, and this one is actually 0.577. This first one was off by 0.8%. The second one was off by 0.6, and the last one was off by 1.6. Now, all right, great, Spainhour. Why did you do all this? Well, this is how they determined these ratios. When I was in high school, I thought, like, when I punched in cosine of 30 degrees into my calculator, I thought some fancy math was happening. All that was really happening was this old school style of using a trigonometry table. They went over here to this first column, went down to 30 degrees, and they spotted, hey, what's the cosine? That's that middle column, 0.866, 0.866. That is all the calculator is doing. The calculator is pulling that ratio when you tell it the angle. This is the ratio that always goes with these triangles. And why can we hold true to that? Because as we said, every triangle that has that angle is similar and must have the same ratios. Okay, so when we do trig in here, oftentimes we use a calculator, but on our first quiz, we are not going to use a calculator. So what are we going to be using instead? These are the basic triangles. Most people know the basic triangles. 45, 45, 90 is 45 in the corner, 45 in the corner. Aside from both of them is a 1, and the hypotenuse is root 2. 30, 60, 90, the small angle is apart from the small side. Hypotenuse is 2. Big angle apart from the big side over there. So obviously that can be written differently. Most people are used to the first two. If you struggled on all, you probably don't know the 3, 4, 5 triangle, and that refers not to angles like these are over here, but instead to the actual sides, because those are clean, which means the numbers are not. Now, oftentimes when you see this written, this is pretty darn close to 37, and this is pretty darn close to 53, so a lot of people will write them like that as well. You could also write them with more decimals as well. But what I could then say to you on your trig quiz is I could say, all right, what is the sine of 45 degrees? And what you would do is you would say, okay, the opposite of 45 degrees here is a 1, the hypotenuse is 2, and the answer is 1 over root 2. Now, if you're watching this video and you're not in my class, I can't speak to this for your teacher, but from my class, I am fine with this being as simplified as you need. If you really want your radicals on top to write that root 2 over 2 and do all that work, that's fine. I know your math teachers push that. I'm not going to concern myself specifically with it here. Okay. Or I could say something like, hey, what's the tangent of, well, actually, no, let's go 30, tangent of 53.1. Now, 53.1 is up here. Okay, so the opposite is going to be 4. And the adjacent, the adjacent is going to be 3. So there is the tangent of 53.1. Okay? You might note, by the way, that this 3, 4 triangle is the small triangle that we had on the first page. So this 37 degrees is actually what this angle was here the entire time. Now, One thing that might make this a little bit wonky or weird for you is I could also ask, what is the, let's say, cosine of 120 degrees? To which you go, 120 degrees is not up there until you think about an xy axis. And okay, this first corner right there is 90. I've got 30 degrees left over. Okay, and so there's my line. I'm not doing a great job with this. That is 120. Now, whenever we make triangles in here, since it's measured from the x, we always draw it like this. Okay, and if that's 120, that would make that 60. The hypotenuse is always going to be positive, it's 2. But the x and the y both have the possibility of being negative. In this particular case, we can see that the y goes up, so that is still positive root 3. But in this particular case, the x, or the adjacent, is that negative 1. So what's the cosine of 120? What's the cosine of this triangle? So the adjacent is negative 1 over 2, or negative 1/2. I'm going to try this again. Feel free to pause the video and try to do it yourself, but pretty quickly here I'm going to go over the answers. Okay, so we could try, for example, the sine of 225 degrees, or we could do the tangent of, let's see, what should we do? We should do 300, and oops, that was dumb, 306.9 degrees. So pause here, see if you can't try to do it. And now I'm going to go over it. 225, let's set up my xy axis here. That's 90, that's 180. Do the math pretty quick, I got 45 left over. So this is a 45, 45, 90 triangle, which means that that is root 2. That's always positive. And these are both going to be 1, but x is going to be negative 1 because it's left. And y is going to be negative 1 since it's down. So the sine is going to be this. So this should be negative 1 over root 2. Once again, I'm completely fine with you leaving it as, that's not very clear. Hold on. Negative 1 over root 2. I'm fine with you leaving the radical in the bottom if you want. Tangent of 306.9. Let's move this real quick. Again, 90, 180, 270. Let's figure out what's left over. What's left over is 36.9. Just going to go here, draw a triangle. If that is 36.9, then that is 53.1, which means that's the large side. So that's 4, 5, and 3. The 5 is always positive because it's the hypotenuse. The 3 is positive because it's right. We have a negative on the 4 since it's down. And tangent, take the opposite, negative 4 over the adjacent of 3. All right, so that's how you get basic triangles in other quadrants. Let's do a problem finally. Now, honestly, if you understood everything I said here, this problem should be relatively easy. So here we go. I have a problem, and I am not going to worry at all about doing, excuse me, a calculator. So this is exactly what you would see on a test, something like this. Here we have a flagpole of an undetermined height that we're going to figure out in a second. We have measured that this on the ground, the shadow is 12 feet long. And we also used a sextant to figure out that the angle is 30 degrees. So what I do is I figure out what sides I want. In this case, it would be the opposite and adjacent. And I draw the tangent of 30 degrees. And this is that ratio. Okay? I can come back over here and move up here and see that the tangent of 30 degrees is the, oh, no, I screwed up, 1 over root 3. So this ratio is 1 over root 3. And I simply set this ratio equal to the ratio in my problem. We're going to call this, actually we'll call this height. So over height over 12 feet. Now the math's pretty simple. Multiply 12 on both sides and you end up with the height is equal to 12 divided by root 3 feet. Is your answer. Pretty simple. The main thing is the work of setting up this ratio compared to this ratio. For me, if you show this step, great. If not, this is the answer. And again, radicals in the denominator are fine by me. There's going to be teachers that disagree with me on that. All right, a couple of quick other things finishing up. Okay, for starters, let's talk about something you're going to see on the homework. Okay, this is such a small thing, and on the homework, I'm completely fine with using a calculator. As a matter of fact, you're going to want to use a calculator. Okay, a lot of times you might get a problem like that, and it'll say something like this. It'll have like a declined angle, and it'll say, hey, that angle right there is something like 0 degrees and 70 minutes. Oh, sorry, not 70. Definitely not 70. Let's go 50 minutes. You're going to say, well, that's dumb in just a second. A minute is simply a fraction of a degree. So all you're going to do in that case is turn the minutes into a degree. And there is 60 minutes in 1 degree. So all we're going to do here is take 50/60ths. And that's going to be my new angle in degrees. And then you can just go ahead and use this fraction in the rest of your problems right up here. And that's fine. So again, if you see minutes, just turn it into a fraction, then turn it into a decimal. I don't have 5, 6 memorized off the top of my head. But yeah, something like, what is that, like 83%, I think. Yeah, it's like 0.83. So this is going to be 0.83 degrees. Okay, 2 more things and we're done. Do I have it on this one? Nope, not that one yet. So, the next basic thing that I want to talk about is inverse trig. Basically, regular trig is this. Give me an angle. Sorry, I put my angle into the calculator, it spouts out the ratio. Or, in the basic trig, sorry, in the basic triangles, I use my angle and it spits out the ratio. Same thing. Okay? This is cosine, sine, and tangent. Now, when I say inverse trig, there's like 2 or 3 ways that you can do this. For starters, if you go all the way back to the beginning, I kind of talked about this at the beginning when I said how many combinations of these numbers there are. There are technically 3, or 6 if you flip them. So hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite are technically different ratios, but they don't do that much different. This is what we call cosecant, secant, and cotangent. We are not going to worry about those in this class. Sine, cosine, and tangent work perfectly for what it is that we want to do in here. So what inverse are we talking about? Well, the inverse we're talking about is not the opposite ratio. What we're talking about is giving the problem a ratio and asking what the angle is. This would be your inverse cosine, your inverse sine, and your inverse tangent. So like I said, if you said, for example, what is the tangent of 36.9 degrees, you would pull that opposite side and it would be 3 over the adjacent side is 4. This is starting at angle and going to the ratio. So what is inverse tangent? Well, inverse tangent would be if we already knew the problem had 3/4 and we didn't know what this angle was. So what we would do is we'd take the inverse tangent, cancel, and then we'd come over here and take the inverse tangent of this guy. And what we're punching into our calculator is we're saying, hey, calculator, if that's the ratio, what angle gives us that ratio? Now, obviously, you can see it's 36.9, but how can you figure that out potentially in the future? Well, tangent is opposite over adjacent. So draw your triangle. The opposite side, let's draw a line here. The opposite side is 3. The adjacent is 4. Now I can recognize that that side's 5. What angle gives me 3 over 4? Well, that angle is 36.9. Now you're welcome to punch that into your calculator when you can't do this with basic trig or with basic triangles. But yeah, so let's do another one real quick. What if I said the inverse cosine of root 3 over 2? Well, then that's adjacent over hypotenuse. So I would draw the adjacent is root 3. I draw the hypotenuse as 2. I know I can complete that's 1, but what angle makes that happen? 30 degrees. You can also do this with other quadrants. So if I said the inverse sine of, say, -1 over root 2, what I would do here is I would assign the 1 to the top. So the opposite side would be -1, so it would go down -1. The hypotenuse would be root 2, so my angle in that case would be -45 degrees. Okay. Final step here is to talk about trig for 0 degrees, 90 degrees, 180 degrees, and 270. Up here on this quadrant, I've drawn 3 lines. Ideally, within my terrible artistic skill, they are all the exact same size. Okay? If they're not, I'm screwing up. And then I'm going to draw a y component on each of them. And what I want to point out is as the angle goes from a bigger angle to a smaller, notice what happens to the adjacent side. Here is the adjacent side of the first triangle. Here it is for the second. And here it is for the third. You can see the adjacent side is getting bigger. Or we'll call this the x in this case. Now, no matter how big it gets, it's not going to be bigger than the hypotenuse. But what if the hypotenuse lay perfectly along the line or at 0 degrees? 0 degrees, or the trig at 0 degrees, is simply doing this. It's saying how much of this magnitude of this line is on the x? Answer is all of it. How do we get the cosine? Adjacent. How much is on the adjacent? Positive r. How much is the hypotenuse? R. Now, don't overcomplicate this. I hate doing this math and then people worry about this. Really, all I just said was, hey, this straight line going right is actually a triangle. It's just that one of the sides is 0, which brings me to the other piece of this. As we were going from this bigger angle down to the smaller angle, what happens to the y side? Well, you can see, okay, start off kind of big, we get smaller, and then as it lays perfectly along 0 degrees, how much is the y side? Well, the y, or the opposite side, there's none of it anymore. It's become 0. So what's 0 over r? 0. What do these answers really say? What these answers say is how much of that line is on the x? 100%. How much of it's on the y? None. By that logic, we can come up here to 90 degrees. What if the line was straight up? Let's go the opposite way with it. 1, you can see that the adjacent side, which was bigger all the way out here, is now getting smaller. And as we get to 90 degrees, none of this is on the x. All of it's on the y, or the opposite side. So the cosine of 90 degrees, the adjacent is 0 over r, or none of it's on the x. How much of it's on the y? All of it's on the y, so plus r over r is 1. Now, there is a little bit of a weird exception over at 180 and 270, so let's talk about it real quick. What is the cosine of 180 degrees? Well, you remember I said earlier that the hypotenuse of a triangle, let's call this r, cannot be negative, but the x and the y can. So in this case, the x is going left, so the adjacent side is negative r over the hypotenuse of r. And once again, people confuse because why are there 2 r's here? Well, it's just represented by the exact same number. This guy says how much of it's adjacent, or on the x, r, going in the negative direction. And this says, hey, how big's the line? Also r. So the cosine of 180 is -1. And you can probably figure this out, so I'm not going to do all the work on this. Sine of 180, how much of its opposite? None of it. See if you can't pause the video real quick and get the answers for 270. But here we go. Cosine of 270, how much is on the x? None. What's the opposite? Well, all of it's on the y, but it's going in the negative direction. And there you go. If you understand all parts of this particular video, this is the trig that we're going to specifically do in this class. If you have any individual questions, please let me know. But I think this will do it. Thanks, guys.